Hi, everyone, and welcome to Fine-Tuning LLMs with 10 Lines of Code. My name is Greg Loughnane, and I'm the head of product and curriculum at FourthBrain. We really appreciate you joining us for today's event. If you're with us live, then good afternoon. If you're near me, I'm in Ohio in the US. For the rest of you, good morning, good evening, or thanks for staying up. Please say hi and tell us where you're tuning in from in the YouTube live chat. We're glad to have you. Today, you'll learn how easy it can be to fine-tune large language models, or LLMs, using an open source framework called Ludwig. Piero Molina, the CEO of Predabase and creator of Ludwig, will teach us how it's done using a simple declarative programming approach. By specifying your inputs and targets from a data set and the architecture that you want to use, the Ludwig framework can help you generate a fine-tuned LLM for your application in just a few lines of code. Lastly, you'll learn how to leverage Ludwig beyond natural language and LLM machine learning tasks, bringing the big idea behind the framework of declarative ML full circle for you. I'm excited to get into it today and demystify LLM fine-tuning and declarative ML. If you hear anything during our event that prompts a question you'd like to ask the speaker or members of the Predibase or FourthBrain teams, please post directly in the YouTube live chat. We'll do our best to answer all of the questions asked, either directly in the chat or during the Q&A portion of today's event. Without further ado, it's my pleasure to welcome our speaker to the stage. Piero Molina is the CEO and co-founder of Predibase, a company that's redefining machine learning tooling with a declarative approach. He previously worked as a research scientist exploring machine learning and natural language processing at Yahoo, IBM Watson, Geometric Intelligence, Uber, where he was a founding member of the Uber AI organization, and Stanford University. He is the author of Ludwig, a Linux Foundation-backed open source declarative deep learning framework with more than 8,500 stars. Piero, we're really excited to have you. Take it away from here.
Thank you so much for the introduction, Greg. Really appreciate it. Super happy to participate today and basically tell you a little bit about how to train and fine-tune large language models with Ludwig, and also a little bit about the ideas behind Ludwig and how you can apply them to other tasks beyond large language models. Without further ado, let me get started with this presentation. All right. A little bit about me. Greg already introduced me, so I will not waste a lot of time on this. Again, I'm the CEO of this company called Predibase, which is bringing this declarative machine learning approach to the enterprise. And had some experience at Uber as a co-founder of the AI team, and it's where I created Ludwig, really, and also spent some time at the Stanford AI lab. The interesting thing in my mind for of my experience when I was at Uber is that I had experience bringing some machine learning to some real products, really. In particular, I worked in this automated customer support system that was really the first deep learning model deployed at Uber, to the best of my knowledge, a fraud detection model that identified the collusion between drivers and riders, and also a recommender system for Uber Eats. And so if you ordered some food from Uber Eats and you clicked on one of the suggestions, there's a little bit of my work also that went into that. The important thing about this is not the specific projects, but the fact that by working on all these projects, I distilled what I learned from working on them into this library, Ludwig, that I'm going to tell you in a second. So the agenda, also Greg already mentioned it. Let's first talk about fine-tuning language models with Ludwig. Then let's talk about the declarative machine learning approach in general, and then how you can apply that beyond NLPs, also to other tasks. Let's jump right into it. All right, so what are the problems with fine-tuning large language models? In particular, they are really, really powerful models, but they're not that easy to use, and they're easy to adjust and apply to your use cases. And so in many cases, you actually need to write a lot of code. You need to write some data preprocessing, some training code, and also things like checkpointing. And because they are large, they need to be trained on clusters of machines. So you need to manage those machines and also figure out how to run the distributed training on top of these machines. And building all of this is time consuming, and also it's error prone. You need some certain degree of expertise to be able to get it right. And so we are going to use Ludwig to try to simplify this. But what is Ludwig to begin with? Again, it's a low-code declarative framework to build deep neural networks. And the way it works is that you basically specify configuration files instead of low-level machine learning code. You can extend it with low-level machine learning code, and we will see how a little bit later on in the presentation, but you don't have to begin with. It supports also multitask learning and mixed modalities, which is something that is not always super easy to do manually. And it was developed and used in production at Uber when I was there. And also now it's backed by the Linux Foundation. And you can find it on GitHub, and there's more than 100 contributors and a growing community. So you're welcome to participate and join us. So how does it work? Again, the basic idea is that you can specify just a declarative configuration that defines the task that you want to solve. An example is what you can see here on the left-hand side. It's very easy to start because basically all you need to specify are the inputs and the outputs that your data contains and that you want your machine learning model to actually learn to predict. And so in this case, we're starting from like a simple text classification example, where you have an input that's a sentence with type text and an output that's an intent with type category. The type is very important. We will see later specifically why, but it basically defines how the data is going to be pre-processed and what kind of architectures are going to be used for, in this case, encoding text and for predicting categories. The data type of the output defines also the task that we're performing. If it was a number, then it would be like a regression problem, or if it was like a set, then it would be a multi-label classification problem. In this case, we're talking about just a simple category. This is literally all you need to do to train a deep learning model for doing text classification. It reduces the amount of time that it needs you to actually build such a model from potentially months to days, really. Or, I mean, writing the first version is really a matter of seconds, but iterating usually takes a few days. You don't need to write a low-level machine learning code, and it's also readable and reproducible. At the same time, it guarantees a level of control that experts may want to use. There's more than 900 different parameters that can be changed in the configuration, and those include all sorts of things, from which architecture to use, to what are the training parameters, what are the details, all the way down, if you want, to the single activation of the single layer of the model that you are training. But also contains pre-processing parameters, training parameters, and mechanisms for running hyperopt and distributed training. So it's very, very rich, and you have full control. The nice thing is that it makes it very easy to iterate. So, for instance, changing from using an LSTM to using BERT is just changing one string in the configuration file. So you have an entirely new model, and you can iterate and improve the models for your task very quickly. It's also extensible. I will show you how, but you can basically provide your own custom Python code in the form of a Python class, register it, and it becomes available from the configuration. And it also bakes in a bunch of advanced functionalities, for instance, hyperparameter optimization, or the state-of-the-art models, in particular, text encoders, image encoders, are all available out of the box. You don't need to re-implement them. And it also supports distributed training very easily, and we're going to touch on that too. But let's look at how you can use Ludwig for fine-tuning large language models first. So here on the left-hand side, I'm showing Ludwig configuration, and it's basically the same that we had before, but here I changed a couple things. So, for instance, in this case, in this case, I decided to use BERT as the encoder for for the sentence, for the input text. And I decided to change the learning rate, and I set it to a really low value of 0.00002. The reason is that when you are fine-tuning a large language model, there's a lot of knowledge and information is already baked in the model, and using large learning rates will make so that the model will forget what it had learned before, and this is a phenomenon called catastrophic forgetting. And by using very small learning rates, you basically are fine-tuning the model without losing all the information that it had accumulated previously when it was first trained. And so as you can see, you only need 10 lines, not even of code, of just a YAML configuration, really. You don't need to write additional code to fine-tune a BERT model. And I'm going to show you in a notebook in a second how that actually works in practice. At the same time, you have additional capabilities in Ludwig to make training substantially faster. In particular, fine-tuning BERT, depending on the hardware that you have at your disposal, may require some time. If you want, though, to just use BERT as let's say, a frozen encoder and caching the embeddings that you're getting from BERT, all you need to do is to specify that you don't want the BERT part to be trainable, and that you want to cache the embeddings with this pre-processing cache encoder embeddings equals true. If you do that, basically at the first epoch, the Ludwig process will generate the embeddings from BERT, cache them, and then reuse them at the following iterations, and that speeds up the computation dramatically. Also, here I added a few more parameters that are particularly good for fine-tuning. In particular, some options for the learning rate scheduler. One is warm-up. So when you start using and fine-tuning large language model like BERT, what you need to do is you need to slowly increase the learning rate to the actual value that you want to use, and that fraction makes it possible to increase the learning rate for the first 20% really of the first epoch. And also the decay parameter makes it possible to gradually decrease the learning rate over time linearly, and that helps a lot with the stability of the training. Finally, there's two more parameters that I'm modifying here. One is the optimizer, and so ADAM-V has been shown in literature to be more effective than other optimizers at fine-tuning specifically. And finally, if you want to increase the performance of the speed of how the models are trained, you can turn on mixed precision, which again decreases the time that it takes to train such models. If you want to train substantially larger models than BERT, BERT is like a pretty large model to begin with, but recently in the last 2 or 3 years of research, there have been many models that have been proposed that actually go past the barrier of the billion parameters. And some of those are also open source. And so those are the ones that you have access to in Predibase. And so, for instance, you can have models that go beyond the size of the GPU memory, like OPT or Flantify or Bloom. And the way to use such models in Ludwig is just specifying the type in the encoder section of the input sentence in this case, and to specify a slightly different backend for training. Because these models do not fit in the GPU memory, you need to use multiple GPUs. And the way we do that is we use Ray as an abstraction over multiple GPUs, over really a cluster of GPUs. And you need to specify the trainer strategy, FSDP, which is a strategy that makes it possible to slice the model across multiple GPUs so that it fits in the sum of the memory of your cluster. Great. So now let me show you these things through a notebook. Let's dive into the code. Okay, let me scroll to the very beginning. So this notebook will be available after this presentation, and will be available on the Ludwig.ai website. So if you search for it, you will find it there. The very first thing to do is to install Ludwig, and here we're installing the very latest version from the live Git repository. And after you do that, we're downloading a dataset. The dataset that we are using in this case is this AGNew dataset, and this is its structure. So it contains like just a class index and a class, and the types are basically a world, sports, business, and sci-tech. Those are different types of news. And for each single news that we have in this dataset, we have both a title and a description. Here, there's like a handy function in Ludwig so that you can just call agnews.load with the split and then see what's inside the split. And as you can see here, we have like titles, descriptions, and the class, which is what we want to predict. In this, the first 5 are all like sci-tech news, but there's also sports news and business news and world news in the rest of the dataset. And so here, let's see how we can use Ludwig for training a model with an LLM on this dataset. So the configuration here is the same that I was showing you before, but here it's like written in the form of a Python dictionary instead of a YAML file. But they you can imagine that those are basically equivalent. This is if you have a YAML file, this is like the parsed YAML file, really, right? With respect to the example that I was showing before, the only difference is that, first of all, we have 2 input features. The first one is the title, and the second one is the description. And for the first one, we are using BERT and making it trainable. For the second one, instead of using another encoder, we can use the same encoder of the other input feature, in this case, title, by specifying that these 2 features are tied. So we will do the same pre-processing and use the same encoder in the model. Then here I also added all those additional, refinements that we're showing in the previous slides, in particular the use of ADAM-V, the use of mixed precision, and the improved rolling relate scheduler with the warm-up and the decay. Once we have this configuration, we can create a model by just initializing this Ludwig model class by providing this configuration that we just created. And we have a model ready here. To train the model, we just call the function model.train, and we provide as dataset the training dataset. What this produces is a bunch of training stats that we're going to look in a second, the data in a preprocessed structure, and also an output directory where the model is saved. This is what Ludwig basically prints while it is training. Let me go from the very beginning here. So first it gives a little bit of description of the experiment itself, and then provides information about the configuration that we are using. And then there's a section of pre-processing. And finally, this is like some specifications of the dataset. And then finally, we start the training section. And we basically train for 3 epochs because I set that as a maximum. If you train for longer, basically you could get even better performance. But I limited to 3 epochs just for for explanation purposes. And basically, after each epoch, you can see the performance of the model. And you can see after the first epoch, we have on the training set an accuracy of 78%, and the validation set an accuracy of 88%, and 87% on the test set. And then we keep on training, and performance improves over time. It starts very high because we are reusing BERT as an encoder, and so the model is very capable from the very beginning because of the weights that we are loading. And then we look at we run this evaluate function, which basically makes it possible to have some test statistics and the predictions from the model. You can also call model.predict to just get the predictions without the test statistics. Evaluate assumes that the data that you're providing also has some ground truth to compare and compute the performance. And here you can see all the statistics that are generated for you. So there are statistics that are like the let's say overall over all the classes, and also statistics that are for each single class. So you can see how accurate the model is for each single class, and all these additional statistics like the hit rate, the false positives, and recall precision. Everything is available. Great. And now that we have, these evaluations and metrics, we can also visualize them. First, we need to install this dependency. And then Ludwig basically makes it very easy by packaging in some visualization functions already to just show what the performance of the model is. And so, for instance, here we're importing this confusion matrix function that basically takes as input the test stats that we have computed previously, and also the metadata that we have computed previously, and basically generates confusion matrix like this, where you can see that the performance on the diagonal, meaning the correct prediction both of what the actual class is and what the predicted is very high, and there are a few little errors across the different classes, but overall the performance of the model is very good. And this is like a Breer score, basically ranking the different classes by the entropy of the predictions. And another nice thing that Ludwig has baked in is the possibility to show the learning curves. And here, by just loading this learning curve function and providing the training stats, you will see like the performance overall, the training and the validation set over time. This is for the different metrics. So first accuracy, then it's at K, and there's also the here the loss over time. Great. So now that we have this model and we looked at it and we like it, we can use it for producing predictions on new data. And so here I'm creating this data frame with 3 data points. The first is a news about the NBA playoffs. The second one is some news about Google, and the third one is a news about politics and Europe, the current situation in Europe and Ukraine. And so you can call the predict function over the model by providing this data frame that we just created to look at both the predictions and, if you want, optionally where they are saved. And so if you look at the predictions, you can see that it contains the actual predicted class. So sports for the first news, sci-tech for the second one, and world for the third one. The probabilities of all the classes. This is the probability of the class that was predicted, which is pretty high. So the model was pretty confident that this was the correct class. But also you can see the probability for the other classes. Nice. So the next step in this tutorial is to show you how to train a different model. In this case, the model that we have here is a model where we set trainable to false. And so it's a model where we're not fine-tuning the actual BERT original architecture, but the original weights. But what we are doing here is we are doing just transfer learning, really. And all the other parameters are the same. And so you can see here that you just change one parameter here, trainable really, to false in the, and also the cached embeddings to true. And this is all you need to change to basically completely change the behavior of Ludwig. And all the rest is exactly the same. You create a new model, and then you call model.train. And you can see here the process working. And finally, this is like an example of how to train a model on multiple GPUs. We're not doing it in this environment because Colab doesn't allow you for multiple GPUs. But if you have multiple GPUs at your disposal, you can definitely run it. And here you can see that we are using the Big Science Bloom 3 billion parameter model. And you just need to specify what is the name of the model, and in this case, set it trainable to true. And the other big difference is that in the backend, you need to specify that you want to use Ray and that you want to use the FSDP training strategy for distributing that, the slicing the model and doing model parallel training over multiple GPUs. Great. So hopefully this was useful and clear. And now I'm going to move towards doing one step back and talking about why declarative machine learning and how this under the hood, a little bit more under the hood, this mechanism of defining configurations really work and what's the architecture behind it. Yeah, so the basic idea behind declarative ML is that today, machine learning in the enterprise is done in two ways, really. One is by using low-level machine learning frameworks like PyTorch, TensorFlow, Scikit-learn. And on the other hand, there are AutoML tools like DataRobot, H2O, and Google AutoML tables. Both of these approaches have their limitations. My experience when I was developing those products that I was mentioning before at Uber is that the first one that I trained was this intent classification model for customer support, and it required 5 months of development and 7 for deployment and a lot of lines of TensorFlow code. Then the second one was a fraud prediction model that this time around was a new code base written in PyTorch, and it required 5 months of development and 4 of deployment. And then the product recommendation was even longer development time. So each of these projects took too long to deliver value, and there was never enough machine learning resources to support the breadth of projects that the company wanted to do. And the tools were too complex for non-experts to use. And so then I had this idea of, well, let's try to build a tool that makes it substantially easier for non-experts to actually do that. And when I looked around, there were these declarative interfaces and systems that made complex tasks easier. For instance, dbt made data engineering substantially easier for analysts. Terraform made the management of infrastructure substantially easier for DevOps teams. And so what can we do for making machine learning substantially easier for engineers? And that's how I came to the conclusion that the same declarative approach that Terraform uses, and also similar to what dbt does, by providing a declarative interface and a configuration, was a way to simplify that substantially. And so by adopting this approach, you can basically get the best of both worlds, right? You can get the flexibility of the low-level machine learning framework together with the simplicity of an AutoML solution. And so this low-code automation basically reduces time to value and both opens up the door for engineers to do more machine learning, even those ones who are not super experts in machine learning to begin with. And at the same time, if you have expert data scientists, they can control everything that they want. As you've seen, the configuration system is very, very rich and gives you a lot of possibilities. And so this kind of approach has been adopted in multiple leading AI tech companies. First of all, obviously at Uber, where I developed Ludwig originally, and then I made it open source while I was there. But there was also this system, there is also the system called Overton at Apple that serves billions of queries, and it was developed by Professor Chris Rea from Stanford, who is also one of our co-founders. And another system that has been developed at Meta called Looper that serves more than 700 models with more than 4 million predictions every second. And these are all like closed source systems, both Overton and Looper, while Ludwig is the only open source one. And what we're building at Predibase builds on top of it. So it's the first open source based system available for the larger enterprise space. And so what are the capabilities behind the scenes that are there in Ludwig that make it possible to use it for both fine-tuning large language models, but also beyond NLP? So the underlying architecture of Ludwig is what we call ECD, for encoder combiner decoder. And it's a really general architecture that then for every single problem can be instantiated to produce a specific type of machine learning model. The way it works is that each single model is composed of multiple encoders, and these encoders have a data type associated with them. So for instance, there could be an encoder for text, for categories, for numbers, for binary values, for sequences, for vectors, for sets, bags, images, time series, audio, speech, H3, which is a geospatial data type, and date. And basically, you can have multiple of these in your model. The data is encoded and transformed into a vector by a piece of the larger deep learning architecture that you want to use. All these vectors are then provided to the combiner, which aggregates them and then provides them to the output part, which decodes the information from these vectors into either text, categories, numbers, binary values, sequences, vectors, and sets, which basically means all the tasks that produce these kind of values are tasks that are supported by this architecture. Each single data type could have multiple encoders. As we've seen with text, for instance, you could use BERT for encoding, or you can use Bloom for encoding, or you could use like even models trained from scratch, like LSTMs or CNNs. And the same is true for all the different data types, including images, where you can use ResNet, you can use VIT, or you can use EfficientNet. They're all basically options in the configuration. And the nice thing is that depending on the specific definitions of your configuration file, you can do a different machine learning task. So for instance, the example that we've seen so far was a single text input and a single category output, but you could provide an image as input and text as output, and you will have an image captioning system. Or you could provide multiple tabular data types like categories, numbers, and binary values, and a number as output, and you will be doing basically just a classical regression problem. Or you could have audio or speech as input and a binary value as output for doing speaker verification. And even more complex tasks where you have text as input and image as input and an output, either binary or class, or either binary or category, which will allow you to do visual question answering. As you can see, the combination of inputs and outputs is what defines the task. And so literally it's your creativity and the data that you have available is the only limit here. And this is an example that puts it all together. It's an hypothetical example, but it's something that, like sums up many of these capabilities. So in this example, you can see a configuration where we are trying to predict the genre and the price of a book. And the information that we have about each book is its title, the author, the description of the book, and the cover of the book. So the title is encoded as text, the author as a category, the description is again another piece of text, and the cover is an image. And what we are predicting here is the genre of the book as a set. So books can belong to multiple genres. There could be like a sci-fi noir book, for instance. With set, you basically can do multi-label classification. And the price, so it's a numerical value. And the nice thing about defining an architecture like this is that it's both multimodal in its nature, but also does multitask learning. So you train one single model to perform both tasks at the same time, both predicting the genre and the price. This seems too simplistic, but in reality, as we have seen up until now, you have a lot of way to influence both the model, the preprocessing, the architecture, and basically all aspects that you want of your machine learning model that you are training. And so, for instance, here we have enriched the configuration by specifying that we wanted to encode the text of the title with an RNN with using an LSTM cell with 2 layers with state size of 128. And we wanted to use a specific tokenizer for preprocessing this text, which is space-punked. There's several that you can choose from. For the author, we're going to use an embedding layer of size 128, and we're going to only retain the 10,000 most common authors, and collapse all the others into rare classes. For the description, we're going to use BERT, and for the cover image, we're going to use a ResNet with 18 layers. For preprocessing of the numerical values of the price, we can do this score normalization as a preprocessing step. And we can specify all sorts of training parameters like the number of epochs, the batch size, which optimizers to use, and its parameters, the learning rate, and so on. We can also choose a backend. We've seen how to specify like a array backend, but you can also specify a local backend to run on any machine, any local machine that you have at your disposal. And you can also specify an hyperopt space by defining which metric you want to optimize, what sample to use. Here you can see the random one, but there's also Bayesian optimization and evolutionary and genetic algorithms that can be chosen here. And the ranges of the hyperparameters that you want to test. For instance, in this case, the number of layers for encoding the title and the learning rate. But you can define your own the way you want. So as you can see, there's a lot of flexibility in the configuration file, and you can do almost everything that you will want to do by hand. Additionally, if there is something that is not available in Ludwig that you may want to use, like for instance, a specific encoder that is not there, or a specific loss function that is not there, or anything like that, there's plenty of developer documentation on the website that define how we have this concept of abstract classes in Ludwig that you can extend very easily. And here on the left-hand side, you have an example of how to extend an encoder for text. And you can create a class called myEncoder that extends the encoder. And you need just to provide two functions, the init function with the parameters of this encoder, and the forward function that takes the inputs, does some computation with PyTorch, and provides a vector out. You can see that it is very flexible. So literally any piece of deep learning architecture could be fit into this kind of framework, really. And then all you need to do is to use this decorator for registering it with a name. And once you do this, from the configuration, you can specify encoder type myEncoder. And so you're basically extending the platform very easily. And here you can see like a little bit of a screenshot of Predibase, which we're building again on top of Ludwig. And you can see how in the UI, the encoder that you specified becomes one option from a drop-down menu. The very last part that I will want to cover with respect to Ludwig is how to scale it up to larger size. How does it work? And so this is a general scheme of the architecture of the Ray backend that you have seen in the examples at the very beginning. And so what happens here is that the Ray backend makes it possible for us to both do data parallelism, where the data frames that we're using as input are sharded across different workers, and also model parallelism, where you have the models that could be split across multiple GPU machines. And this is all tied together by the using of Ray that makes it possible to run this at a large scale. The way to do it is pretty simple. You can just specify in the configuration the fact that you want to use Ray as a backend, and then you can specify what are the resources available for the training. For instance, if you wanted to train the same model that we were training before on 64 machines, each of them having resources with one GPU, obviously you need to have availability of these resources, but if you have that availability, setting it up is as simple as specifying how much of it you want to use. And this makes it scaling to larger, both larger data sets and also larger models really, really easy. This is just from a configuration parameter. And the same thing is true also for HyperOpt. We're using RayTune behind the scenes. That makes it possible to run all the different tasks of the HyperOpt job that you're defining in parallel in a way that is very, very scalable. And I've already shown you the configuration for doing that. It's very easy. You just specify the space and the optimizer that you want to use from the ones available in RayTune. And then very quickly, I want to tease you a little bit what Predibase does with respect to declarative ML. And it's basically the first enterprise platform that brings all these ideas that are there in Ludwig and this configuration system, but makes it available for enterprises. At the core of it, there is like a model training component that's built with Ludwig, but we basically are building a bunch of additional components. It makes it easy to build models, iterate them, and then deploy them. The first one is a data connector, which makes it easy to connect with data sources such as data warehouses, databases, object stores like S3. There is a notion of a model repository, which makes it easy to iterate over the models, looking at their lineage and collaborating with other people throughout their development. And then we have this SQL editor, which is a new idea. It's basically a declarative language that is a little extension of SQL, where you can write predictive queries in a way that is very similar to what you do in SQL. All of this runs on this managed scalable infrastructure that runs on the cloud providers. And when you are happy with your models, this infrastructure makes it possible to both serve the model in real time and also serve them for batch prediction. And these are the interfaces of the system. You have a user-friendly UI, a SQL-like query editor, where you can write things like predict conversion given the customers in my customers table by reusing the models that we've been trained with the declarative approach of Ludwig. And there's also a Python SDK, which looks a lot like Ludwig, but instead of running locally on the machine where you are actually running the code, runs this on Predibase and keeps track of it and makes it very easy to iterate, collaborating with people. And very quickly, I wanted to show you like the interface of the platform. So here, for instance, this is the way that you can see for how do you connect new data sets from all these different data sources. Here you can see one model repository for a dataset called Twitter bots, and you can see all these different models, their lineage, and you can also very easily diff them because they're all configurations. So maybe the difference between the model number 2 and model number 8 then becomes basically the only difference between these two models is that for this description text, I was using BERT as an encoder, and here I didn't specify, so using the default parameter. And within the model repository, creating a new model is very easy. You can basically just specify what the target is and the architecture that you want to use, in this case, neural networks. And you can see all the features of this data set. And you can basically click next, and you have this abstracted view of the neural network architecture, where you can basically jump in and change everything. For instance, I want to change the tokenizer for the description by using just the characters. And I want to change the encoder here. Instead of being embed, I want to use T5, for instance. And the same is true for all the other features. And I can just click train. And what I obtain is a repository like this, where you can see like the performance of the model over time, and also the learning curves and the confusion metrics and the ROC curves. And basically you have all the controls that you want. And then finally, you can run these queries, like you can look at the Twitter bots dataset, which contains information about a Twitter bot, if it's a user or a bot, their description, structured information, and even the images, the profile images. And by just running predict account type given those Twitter bots entries, you can obtain the predictions from the model with these account type predictions. And even further, you can obtain some explanations of why the prediction was produced by the model by looking at the importance of each single feature for the prediction that the model made. Great. So let's jump back into the presentation. I have just one last slide to show you, which is what we're doing with LLMs at Predibase. The first thing is fine-tuning LLMs, and that's what we've been discussing for all of it today. And it makes, as you've seen, Ludwig makes it very, very easy to do it, and with Predibase, you can do it in a managed way. We're also adding some LLM-based capabilities to the platform. In particular, we have this data science copilot, which is a mechanism where you train a model with a configuration and have some results, and then the data science copilot suggests what are the changes in the configuration you may want to make to improve the performance of the model. And we're also adding this mechanism for compressing large language models without needing label data into smaller specialized models that are as performant as the larger models, which makes them 1,000 times smaller, 100 times faster. You don't need to pay per query like you would do with a large language model API. And also the data never leaves your environment, and the models that are trained are yours. They are not someone else's. So we're very excited about this and curious to get feedback from you. Yeah, so this is all I had. Really hope that this was valuable and interesting. If you want to get in touch, please reach out to piero@predibase.com or for me on LinkedIn. And there's plenty of resources. You can look at the Predibase website where there's like blog posts about all this stuff, the Ludwig AI website where you can see all the documentation around Ludwig, the GitHub page where you can get all the, look at all the code, and the Slack community. If you want to get involved in the open source community, there's a link to our Slack page. And with this, I thank you for your attention, and I'm happy to answer any question you may have.
Piero, that was awesome. Thank you so much for that presentation. I think everybody in the chat was really loving some of the action that you were showing, both open source and also in the platform. Big shout out to the entire Predabase team out there answering questions in the chat as well. I'm going to try to make sure we hit the main questions that haven't been answered. Connor, you've been out there crushing it, so hat tip to you, data scientist at Predibase. But I think we're getting a lot of questions, Piero, about what LLMs does Ludwig support. We're getting a lot of questions about Llama and Alpaca. As somebody that's got a very close ties to Stanford, I think this is what a lot of people want to do today. What do you have to say about sort of ways to go about creating your own, open source LLMs from something like Llama? Is that sort of in the cards for you guys, and what would you do right now?
Right. So we in Ludwig, basically you have really easy access to basically every open source large language model that has been developed so far, in particular the ones that are available on the Hugging Face spaces. They're all like really easy. You just basically specify the name of the space that contains the LLM, and you can directly use it and fine tune it on your tasks. So that's very easy. With respect to Llama and Alpaca, it is so we have there's a mechanism in Ludwig that we are will be there. Like it's working right now in the 0.8 dev version. If it's not available in 0.75, which is 7.4, which is the latest released version. But the mechanism that we already have there, so it's already usable, but in the next version will be officially out there, is you can specify Alpaca as a potential encoder, and you can also specify a prompt they may want to use, which in our experiments helps a lot with increasing performance, because it's a way of conditioning the model to be able to perform a specific task. Let's say, little controversy around it is the fact that the weights of both Llama and, as a consequence, the ones of Alpaca, they have a specific license to be used, and so we obviously don't want to break that license by any stretch of imagination. We want to make sure that you first get access to the Llama weights on your own first, and then you can use them through Ludwig. We don't want to bypass that, right? We definitely don't want to do that.
Right. Yeah, that's great insights. So, I've got a couple other tactical questions here from the audience today. I think Rick got all his questions answered from Connor. So shout out to Connor again. Do you have any sort of hardware recommendations for running fine tuning within like a Google Colab notebook, like the one that you're going to put out later today or tomorrow? Maybe it'll time out on CPU. Do you have any sort of recommendations on how to go about that for folks that don't have a cluster sitting right next to them?
Right. So that's, I would say, for people who have, for instance, one GPU instance and maybe just a Colab availability, Colab has an additional restriction, which is not just the fact that you're using the GPU, but for how long each single task that you're using it for will last. And so that was part of the reason why in the notebook you see me putting like that number of epochs to a small number, 3, because of that, because you don't want to go in the regime of being, basically timeout, really. So the suggestion there is to try to find a good balance between the size of the model and the amount of time that you trained for. For instance, we have found like particularly good results with smaller versions of some of the bigger models. For instance, if you use Dilbert, you usually get a certain percentage of the performance at, half of the cost in terms of the number of weights and the number of parameters. Another example is like T5. T5 has multiple versions. There's the 11 billion version one, and all the way down to the small one, which now I don't remember on top of my head exactly how many parameters it is, but it's like something that fits into a GPU. And so, you can figure out what is like a good compromise there. And the other aspect is, depending on the tasks, fine-tuning the entire model may not be the most, let's say, performance per buck version of what you could do, right? And so in those cases, what I was showing, the second example, the one where you're actually freezing the weights and then just specifying the cached embeddings, that is a good compromise in many cases, because there are, the other parts of the model, the combiner and the decoder, which add a few more layers. And you can specify, by the way, how many more layers you want that are not frozen. And only those are trained, which makes it substantially faster than fine-tuning the model in itself. And in some cases, you can get good enough performance that rivals the performance of fine-tuning. In other cases, fine-tuning works substantially better. It really depends on the the main factor there is how much does the data that you're going to train your model on reflect the data that the model was originally trained on. So for instance, if the original model was trained on like web data and you have like medical records, for instance, maybe there's some distance there. But if you're training on news tasks, probably the model that was pre-trained without even fine-tuning can be good enough, right?
Right. So you're saying that it's not just that there's how much data and how many epochs for fine-tuning. That's not the only trade-off that's going on. You can also go dig into the model and you can say, well, actually, I want to freeze part of it and I don't want to fine-tune the whole thing. And that's going to work better in cases where the data was more similar to the model that was trained.
Exactly.
Wow.
Exactly.
Yeah, that's a key insight, and certainly one that, as people are building these tools, can potentially help save them and their companies a lot of resource dollars. That's for sure. So
and our experiment is 50 times faster, really. So
and then Ludwig sort of allows the encoder decoder stuff to, come in, and that's how you can easily freeze particular parts of it.
Exactly.
Okay. Yeah.
In the encoder section, you can specify this part is like trainable equals false. And so that part will be frozen, right? If you do that with a model that is like trained from scratch with random weights initialization, obviously that, will not help. But if you're doing it with a model like a pre-trained one, where we are loading the weights that have been trained on a lot of data previously, that is useful because then you don't need to fine tune it all the way down, right?
Yeah. Wow. Great stuff. Looks like, Chris, I want to, you're getting a lot of questions answered by Connor in the chat, but I think there was a couple, just at least one quick question on the hyper optimization. Optuna, is that something that works with Ludwig as well? Or I know you mentioned GrayTune.
So we're using GrayTune as our backend for doing optimization, and GrayTune supports multiple both algorithms and library specific hyperparameter optimization libraries within it. If I remember correctly, I believe that Optuna is one of those. So it's one of the options that you could use, but there's a few others, even some commercial ones. But I think the one that we have found to be particularly useful and working particularly well is the hyperbandwidth Bayesian optimization. It's particularly good because of its uses of resources. So at the beginning, it starts with training a bunch of models in parallel. And then depending on the information that it gathers throughout the training, decides which ones to actually stop and which ones to actually create new samples from what, in a Bayesian way, from the information obtained so far. And then basically over time, only the models that are more promising are the ones that are trained more fully. The ones that are not promising are basically interrupted early. And that makes for a really good use of resources, really. And so that's the one that we suggest using as the first approximation. But again, there could be others, and I think also Optuna could be used as one of the mechanisms there.
Nice, nice. Yeah, I just want to kind of move from tactical to some kind of strategic questions. You know, you've been in the game a long time. We've got a lot of learners out there that are kind of maybe early on in their journey, and maybe they're not so deep on all of these details and all of these names. You know, kind of a two-part question. You know, 2023 is crazy with AI. LLMs are all the rage. They're really having their moment in the sun here. How are you following all the advancements in AI today? And what advice would you have for people that are trying to do that? And even for folks that are trying to just get started in 2023?
Yeah, so keeping up with the literature is very, very difficult. I think it's an unsolved problem. If someone tells you that they solved it, I think they are lying to you, honestly. My way of doing it is, you know, I'm blessed by the fact that, you know, I'm that attached to the Stanford AI lab, and my way of keeping up is by looking at what the students in the lab actually pay attention to. That's very, very, I mean, it's not 100% of what I also pay attention. There are things that I directly pay attention to, but, you know, they keep me honest, right? They keep me, they're kind of like a collective filter for me of what's particularly interesting and the newer developments, right? But something that everybody could do, even if they don't have access to that, there's many resources if you want, and you know, shamelessly like plugging one of the one that was, you know, participated in creating, which is this seminar series that I previously was running at Stanford. It was called the MLSys seminar series. And now I'm, you know, not running it anymore. And there's new students in the Hazy lab that are like running it. And the amazing thing is that every week they invite one or two new people to talk about recent advancements. And, you know, for me, that's also previously was a way for talking with interesting people in the space. And now it's a way to keep up with what's interesting in the space too, right?
Yeah,
so,
yeah.
For people who want to get started, though, I think it depends on what goal do they have, really, right? If their goal is to use something, let's say they're developers and they want to add something, some machine learning capabilities to their applications, I would say a high-level tool like Ludwig is a very good starting point, because it's very simple to get started, and then you can learn about the different parameters and the different architectures and all of that gradually, step by step, but already starting getting some value out of it. And it's like a gentler introduction than just being thrown into like using a library like PyTorch and then having to learn about all the details of tensors and tensor computation and all of that. I think eventually, if someone is serious about it, they will want to go all the way down and understand the single computation that is happening. But you know, you don't need to make it hard for yourself from the very, very beginning, right? And then this is for people who want to practically just use machine learning and add machine learning, right? And then there's people who want to do research and learn the details. For those people, like, it's a really different approach. And I would say a tool like Ludwig could still be useful for them to make their life easier and faster, to have baselines and all of that. But for people who want to do research, in my mind, the most interesting thing is actually, and again, this is like a little bit of a controversial point of view if you want, but for me, the most interesting thing to do is to actually look at the historical papers and historical like papers that were really impactful in the field, starting even honestly from the 80s. There's very, very valuable work that was done by them that now it's kind of obfuscated by the fact that we're doing so much more recent developments, but some of the groundbreaking ideas were already there at that time, and looking at them at the source is very useful to then see the progression and understanding the trajectory, right? And so if you're doing research, the trajectory is important because if you know the past and the present, maybe you can at least a little bit have an intuition of what's going to happen in the future and where you should invest your effort.
Yeah, I love it. Maybe we'll have to have you back at some sort of Fourth Brain event in the future to sort of chart the path of AI from the 80s up to now. Very
I will
cool.
be happy to.
Very cool. And I really love this idea of working at the right layer of abstraction as a developer, you know, with Lego blocks, essentially, rather than figuring out all the details of what's within the models first. Starting at that building layer, I think is 100% where we're at in 2023. And I think I heard you right that you said Stanford MLSys is a bit like joining a community that helps you kind of stay up on it. That's one of the things that we've seen over and over again in these events at Fourth Brain and Deep Learning. And, you know, thanks to everybody out there today, part of our community, part of the Predibase community. This is one way that we can all try to keep up on what's going on in the industry and what's going on today. So, you know, thank you everyone for your participation. Again, thank you so much, Piero, for dropping knowledge on us all day long. This brings us to the end of today's event, which again has been brought to you all by Fourth Brain and Predabase. Fourth Brain is excited to announce our upcoming one-day generative AI workshop. It has reached capacity. During the workshop next week, individuals and teams are going to curate data, fine-tune an open source LLM, kind of like you saw today, or diffusion model, deploy a working application to Hugging Face, and finally prompt engineer their way to one really great output for judging. If you're looking to build, ship, and share a generative AI application from end to end, we'll be offering the second evolution of the one-day workshop on Wednesday, April 26th from 9 a.m. to 3 p.m. Pacific. And stay tuned for more comprehensive LLM and generative AI programs coming real soon. One last big thank you to Piero. Everybody smash the chat and say goodbye for today. Thanks to everybody for joining us. We'll see you all next time. And until then, keep learning. Bye, everyone.
Thank you very much. Bye.